1.6 Inverse functions and logarithms. The outline of this video is as follows. We will discuss the crucial concept of one-to-one functions, starting with their formal definition and then introducing a simple graphical tool for identifying them, the horizontal line test. With this foundation in place, we will explore two of the most important families of inverse functions you will encounter. First, we will see how logarithmic functions are naturally defined as the inverses of exponential functions, and we will review the key algebraic properties that make them so useful. After that, we will turn our attention to trigonometry, where we will carefully define the 6 inverse trigonometric functions, paying close attention to their restricted domains and ranges. This path will give us a solid framework for understanding and applying inverse functions throughout our study of calculus. Let us explore a special property of functions called one-to-one, which is essential for understanding how to reverse a function's process. While every function assigns exactly one output to each input, some functions can assign the same output to different inputs. For example, the function f of x equals x squared is not one-to-one because it maps two different inputs, -1 and +1, to the same output value of 1. A function is formally defined as one-to-one if whenever two inputs, say x1 and x2, are not equal, their corresponding outputs are also not equal. A simple way to identify this property is to observe if the function is always increasing or always decreasing over its domain. If so, it must be one-to-one. The essential idea to remember is that for a one-to-one function, no two distinct inputs ever share the same output. The horizontal line test gives us a quick, graphical way to determine if a function is one-to-one, a crucial property for a function to have an inverse. The test itself is very direct. A function is considered one-to-one if and only if every possible horizontal line intersects its graph at most one time. If you can find even a single horizontal line that crosses the graph in more than one place, the function is not one-to-one. This is because multiple intersection points mean that different input x values are producing the exact same output y value. For example, the graph of y equals x squared is a parabola, and a horizontal line at y equals 4 intersects it at both x equals -2 and x equals 2. Be sure not to confuse this with the vertical line test, which tells us if a graph is a function in the first place. In short, passing the horizontal line test guarantees that each output value comes from exactly one input value. An inverse function is a powerful tool because it allows us to perfectly reverse or undo the action of another function. We define the inverse, written as f inverse, with a simple rule. F inverse of b equals a if and only if the original function f of a equals b. This relationship means that the domain of the inverse function is the range of the original function, and the range of the inverse is the domain of the original. For instance, if a function maps an input of 2 to an output of 10, its inverse must map an input of 10 back to the output of 2. Be careful not to confuse the notation for f inverse with the reciprocal, which is 1 divided by f of x. A function can only have an inverse if it is one-to-one, meaning each output comes from exactly one input. In short, an inverse function simply swaps the roles of inputs and outputs. Now I will explain the most important property of inverse functions, which is how they behave under composition. The key idea is that composing a function with its inverse effectively cancels the operation, resulting in what we call the identity function, a function that just returns its original input. First, if we start with an input x in the domain of f, applying f and then immediately applying its inverse brings us right back to x. We write this as f inverse composed with f of x equals x. The same is true in the other direction. Applying the inverse to an output y and then applying the original function brings us back to y. For example, if a function adds 5 to a number, its inverse subtracts 5, so doing both in sequence leaves the number unchanged. Be careful not to confuse the inverse f to the power of -1 with the reciprocal one over f of x. The essential takeaway is that a function and its inverse undo each other when composed. We can find the graph of an inverse function using a simple and elegant geometric method, which is based on the idea of swapping the roles of input and output. Because an inverse function interchanges the x and y values of the original function, every point with coordinates a, b on the original graph corresponds to a point b, a on the inverse graph. This complete exchange of coordinates is geometrically identical to reflecting the entire graph across the main diagonal line, y equals x. For example, if the point 2, 4 lies on the graph of f of x, then the point 4, 2 must lie on the graph of f inverse of x. This reflection effectively turns the domain into the range, and the range into the domain. So to get the graph of an inverse, you just take the original function's graph and reflect it over the line y equals x. To find the formula for an inverse function, we can use a reliable two-step algebraic method. The first step is to take your original function, y equals f of x, and algebraically solve it for the input variable, x. This re-expresses the relationship with x as a function of y. The second step is to interchange the variables x and y to write the inverse in its conventional format. For example, let us take y equals x squared, but only for values of x that are greater than or equal to 0. Solving for x gives us x equals the positive square root of y. Then, swapping the variables gives the final inverse function. Y equals the square root of x. But initial domain restriction is essential, because it guarantees the original function is one-to-one and has an inverse. The entire process is simply to solve for x and then swap x and y. Let us use our understanding of inverses to define the logarithm, which is the tool we use to undo an exponential function. The logarithm with base a is defined as the inverse of the exponential function a to the power of x. This means the statement y equals log base a of x is simply another way of writing that a to the power of y equals x. Because it is an inverse, its domain is all positive numbers, while its range is all real numbers. You will most often see two special cases: the natural log, written ln of x, which has a base of e, and the common log, written log of x, which has a base of 10. For a quick example, the natural log of e is exactly 1, because e raised to the power of 1 gives you e. So the essential thing to remember is that a logarithm is the function that finds the exponent. Now I will cover the powerful algebraic properties of the natural logarithm, which are essential for simplifying complex expressions. These rules transform difficult operations into much simpler ones. The product rule states that the logarithm of a product, like b times x, is equal to the sum of the individual logarithms, the natural log of b plus the natural log of x. Similarly, the quotient rule converts division inside a logarithm into subtraction, so the natural log of the fraction b over x becomes the natural log of b minus the natural log of x. The reciprocal rule is just a special case of this. The most powerful is the power rule, which changes an exponent into a multiplier. The natural log of x raised to the power r is simply r times the natural log of x. For example, the log of 1 million, or 10 to the power of 6, becomes 6 times the log of 10. Be careful not to confuse the log of a product with the log of a sum, as there is no simple rule for the logarithm of a sum. The key takeaway is that these properties turn multiplication, division, and exponentiation into addition, subtraction, and multiplication, respectively. Here I will explain the fundamental inverse relationship between exponential and logarithmic functions, which allows us to rewrite any exponential in terms of the natural base e. Because these functions are inverses, applying one after the other with the same base simply returns your original input. For example, the natural log of e to the power of x is just x, and e to the power of the natural log of x is also x, for any positive x. We can use this property to express any function a to the power of x as a power of e. We start with the identity that a to the power of x is equal to e to the power of the natural log of the quantity a to the power of x. Then, by applying the power rule for logarithms to the exponent, this simplifies to e to the power of the quantity x times the natural log of a ti. For instance, the function 2 to the power of x is identical to e to the power of the quantity x times the natural log of 2. This means every exponential function is just a scaled version of the natural exponential function. We can now derive a very practical tool called the change of base formula, which connects any logarithm to the natural logarithm. Let us start with y equals log base a of x. By the definition of a logarithm, this is equivalent to the power of y equals x. If we take the natural logarithm of both sides of this equation, we get the natural log of a to the power y equals the natural log of x. Using the power rule, this simplifies to y times the natural log of a equals the natural log of x. Finally, solving for y by dividing gives us the formula log base a of x equals the fraction, the natural log of x over the natural log of a. This is incredibly useful for calculation. For instance, to compute log base 7 of 50, you can just divide the natural log of 50 by the natural log of 7. This formula shows that every logarithmic function is just the natural logarithm scaled by a constant factor. Let us make the algebraic properties of logarithms more concrete by using them to simplify a few expressions. First, we see that the natural log of 4 plus the natural log of sine of x combines into a single term. Using the product rule, this sum of logs becomes the natural log of the product, which is 4 times sine of x. Next, for the natural log of the fraction with x plus 1 over 2x minus 3, the quotient rule allows us to expand this into a difference. This becomes the natural log of the quantity x plus 1 minus the natural log of the quantity 2x minus 3. Finally, we can simplify the natural log of 1/8 in 2 steps. The reciprocal rule turns it into the negative natural log of 8, and since 8 is 2 cubed, we can then apply the power rule to bring the exponent down, giving us negative 3 times the natural log of 2. The key is to recognize patterns like sums, differences, or powers, so you can apply the right rule to expand or condense an expression. Now I will show you how to use logarithms to solve for the time it takes an investment with annual compounding to reach a specific value. We start with our model, where the future amount a equals the principal p times the quantity 1 plus the interest rate r, all raised to the power of time t. To find t, we first isolate the exponential term by dividing a by p. Then, we take the natural logarithm of both sides, which let us use the power rule to move the exponent t down as a multiplier. This step gives us our final formula. T equals the natural log of the quantity a over p, all divided by the natural log of the quantity 1 plus r. For an investment of $1,000 to grow to $2,500 at 5.25% interest, we calculate the natural log of 2.5 divided by the natural log of 1.0525, which is about 17.9 years. Remember that logarithms are the essential tool for solving for an unknown exponent in these kinds of problems. Let us derive the universal formula for half-life, which reveals a truly remarkable property of exponential decay. We begin with the definition. Half-life is the time it takes for an initial amount of a substance, y naught, to decay to exactly 1/2 of its starting value. We can write this as an equation where y naught times e to the power of negative k times the half-life equals 1/2 times y naught. The crucial insight here is that the initial amount y naught cancels from both sides, meaning the half-life does not depend on how much substance you start with. To solve for the time, we take the natural log of both sides. This gives us negative k times the half-life equals the natural log of 1/2, which simplifies to negative the natural log of 2. For example, the 14-day half-life of phosphorus-32 is the same whether you have 1 gram or 1 kilogram. The important takeaway is that half-life is always the natural log of 2 divided by the decay constant, k. Let us apply our half-life formula to a real-world example to see how it works. We are given the decay equation for the element polonium-210, which tells us that its decay constant, k, is 5 times 10 to the power of negative 3. To find the half-life, we simply take the natural logarithm of 2 and divide it by this specific value of k. This calculation gives us a result of approximately 139 days. This means that if you start with any amount of polonium-210, in about 139 days, you will have exactly half of it left. After another 139 days, you will be down to 1/4 of the original amount. The essential thing to remember is that the half-life is a constant property of the element, which depends only on its decay rate. Let us summarize the 3 most important ideas about logarithms. First, the logarithm with base a is fundamentally the inverse of the exponential function a to the power of x, which means its domain is all positive numbers and its range is all real numbers. Second, we have 4 essential algebraic tools for manipulating logarithmic expressions: the product, quotient, reciprocal, and power rules. Finally, we saw that any exponential or logarithmic function can be rewritten using the natural base e. Specifically, a to the power of x equals e raised to the power of the quantity x times the natural log of a, and the log base a of x is simply the natural log of x divided by the natural log of a. This means every logarithmic function is just the natural logarithm scaled by a constant. The key insight is that the natural exponential and logarithm are the fundamental building blocks for all other bases. To define inverses for the trigonometric functions, we first need to make them 1-to-1. The original functions are periodic, meaning their values repeat, so a single output can correspond to infinitely many input angles. To solve this, we restrict the domain to a specific interval where the function becomes 1-to-1. For example, with the function y equals sine of x, we limit its domain to the closed interval from -π/2 to +π/2. On this interval, every output has a unique input, which is the necessary condition for an inverse to exist. This same restriction process works for all 6 trigonometric functions, giving us their inverses. We denote these new functions with names like arcsine of x or arcos of x. It is important to remember that the superscript -1 in this notation means inverse and does not mean the reciprocal. By restricting their domains, we can define a valid inverse for each trigonometric function. To define an inverse for the sine function, we must first restrict its domain to make it 1-to-1. The standard sine function fails the horizontal line test, so we limit its domain to the closed interval from -π/2 to +π/2. On this interval, the function is strictly increasing, which guarantees every output value comes from exactly one input angle. The inverse of this restricted function is called the arcsine, written as sine to the power of -1 of x. Since an inverse function swaps the domain and range, the arcsine takes an input value between -1 and 1 and returns the corresponding angle, which will always be between -π/2 and +π/2. For instance, the arcsine of 1 is π/2. Do not confuse the inverse notation with the reciprocal 1 over sine of x. In short, the arcsine of x gives you the unique angle in this restricted range, whose sine is x. Now let us define the inverse for the cosine function, which we call the arccosine. Just like with the sine function, we first need to restrict the domain of cosine to make it a 1-to-1 function. For cosine, the standard convention is to use the closed interval from 0 to pi. On this specific interval, the function passes the horizontal line test, which means a well-defined inverse can exist. This inverse is called the arccosine of x, and it answers the question, which angle between 0 and pi has a cosine equal to x? By swapping the roles of the input and output, we find that the arccosine function has a domain from -1 to 1 and a range from 0 to pi. Visually, its graph is a reflection of our restricted cosine graph across the line y equals x. The important thing to remember is that the arccosine always returns a single angle in the first or second quadrant. Now let us look at the graphs for all 6 inverse trigonometric functions, which are all generated using the same fundamental process. As we saw with the arcsine function, each of these graphs is created by taking the graph of the original restricted trigonometric function and reflecting it across the line y equals x. This reflection swaps the domain and range, giving each inverse function its own unique shape and limits. For example, notice how the range of the arccosine function, shown on the y-axis, is the closed interval from 0 to pi. This is precisely the restricted domain we chose for the original cosine function. You can also see the horizontal asymptotes for arctangents and arcotangents, and the split domains for arcsecant and arcosecant, where x must be less than or equal to -1 or greater than or equal to 1. Remember that the output of each function is an angle, so the key is to understand how each graph visually represents the specific set of output angles for its given inputs. This slide summarizes the official domain and range for each of our 6 inverse trigonometric functions, which are the conventions that make them well-defined. For arccosine and arcocosine, the domain is the closed interval from -1 to 1, and their ranges are the principal angle values we established earlier. In contrast, arctangent and arcotangent can take any real number as an input, with their output angles restricted to specific open intervals that are similar to the previous two. Finally, the domains for arcsecant and arcosecant include numbers with an absolute value of 1 or greater. Their ranges are nearly identical to those for arccosine and arcsine, but each has a single point removed where the original function was undefined. These specific pairings of domains and ranges are the standard definitions that guarantee we get exactly one output angle for any valid input. Let us explore 2 key identities that reveal how the arccosine and arcosine functions are geometrically related. First, the arccosine of x and the arccosine of -x are what we call supplementary angles, which means they always add up to pi radians. For example, the arccosine of 1/2 is pi/3, and the arccosine of -1/2 is 2 pi/3. Their sum is pi. The second identity connects arccosine and arcosine directly. For any valid input x, the arccosine of x and the arcosine of x are complementary angles, meaning their sum is always pi/2 radians. You can picture this relationship as the 2 non-right angles inside a right triangle, which must add up to 90 degrees. The essential takeaway is that the sum of the arcsine of x and the arcosine of x is always the constant value pi/2. Let us bring together the key ideas we have covered about inverse functions. We began with the essential property of being 1-to-1, which means that every output value comes from exactly one input, a property we can verify visually with the horizontal line test. Only these functions have a true inverse, which we write as f inverse. that perfectly reverses the original mapping. The graph of this inverse is a clean reflection of the original function's graph across the line y equals x. We then applied this powerful concept to define two crucial families of functions. Logarithmic functions, as the inverses of exponential functions, have special properties that help simplify complex calculations. Similarly, by carefully restricting the domains of the standard trigonometric functions to make them one-to-one, we were able to define the inverse trigonometric functions. Grasping these inverse relationships is fundamental to solving a much wider range of equations. To wrap up our discussion, I would like you to consider two review questions that test the key concepts we have covered. The first question challenges you to connect a function's behavior to the existence of an inverse. Specifically, is a function that is always increasing guaranteed to have an inverse? I want you to explain your reasoning by using the horizontal line test and the definition of a one-to-one function. The second question is a practical application of logarithm properties. Using only the provided approximate values for the natural log of 2 and the natural log of 3, your task is to estimate the natural log of 72. A good first step is to find the prime factorization of 72, which will allow you to apply the product and power rules. Answering these will help solidify your understanding of both inverse functions and logarithms.